Hi everyone, and welcome to lesson 2.2. Today we are going to talk about the summations of our geometric sequences. Now before we get into full-on summations, let's review from our last lesson a little bit more about our explicit formula, right? So what we notice is our formulas that are in the setup a times b to the x power are our exponential functions. So if we talk about last lesson's setup, we had a first term or an a value, in this case of 8. Our b value was consistently square root of 3 over 2. And again, we had that format for our overall formula that are a sub n, first term, common ratio to the n minus 1 power. This is an example of an exponential. And if we look at this in a graphical format, our first term r to the n minus 1, or in this case x minus 1, zoom 6, we see a little bit of the graph that it might be kind of useful for us to zoom out a little bit, so zoom option 3. And we definitely can see that this is one of those decreasing exponential functions in that format. And again, once we had this explicit formula, we talked a lot about how we can then calculate, for instance, the ninth term using that value, right? And 9 minus 1, so the 8th power, and get, for instance, 81 over 32, our ninth term here, right? Now, we could do that for other formats as well. So for this next example on page 24, they want you to, first of all, calculate the r value. Secondly, then use the explicit formula to calculate the 10th term. And again, using that explicit formula to help you do that. With the first term, r value to the n minus 1. Now, moving on from the explicit formula, how can we use this then to help us derive the summation formula, right? That's where we're trying to go on this with the sum for the geometric. Well, if we look at this table of values, right, they're asking us to go back to that Shelley seashell problem, and if we take our first term and our sum, and we multiply it by our common ratio, what values do we get? Okay, so if we take our first sum here and we multiply that 8 by the square root of 3 over 2, right? What's going to end up happening is that reduces to 4 square root 3. And then again, if we take square root of 3 over 2 and distribute it through this sum that they're giving us from our previous problem, we get 4 square root 3 plus 6. And if we distribute again this times the square root of 3 over 2, we get our next term. We have 4 square root 3 plus 6 plus 3 square root 3, right? We see that sum being distributed on. Now, if we take those partial sums, if we take our sum and subtract away from it those pieces that we were just getting, right? We basically are saying that these are equivalent to each other, right? If we factor out, in this case, our first term, which is essentially dividing everything by an 8, since this is our first term, that will then end up equaling our first term times 1 minus r to the n power. So again, we have that sum minus our r value times the sum. Factor out the 8 from both of those, we get this piece, and then rewrite it in terms of r to the n power. Well, if we do that for the second one, okay, we had 8 plus 4 square root 3, and then minus away the 4 square root 3 plus 6, and it turns into 8 minus 6, which is our first term. If we factor that out, 1 minus 3/4. Well, 3/4 is 1 minus square root of 3 over 2 to the second power, right? And what we essentially start to notice is each time, if I finish this pattern out for us to save us some writing, is that each time these are getting factored out, and we notice that this ends up being the n power. Whatever n we are on, we are matching here to this power, right, with that first term factored out on the outside. And again, all of these are equal to each other because of the transitive property, right? We know that these are equal. And if we start using these results, again, and the fact that they are equal to each other, if we see at the bottom of page 25, we have that S sub n minus our R value S sub n equals, again, that last column. And if we rearrange this, if we take out this GCF that they both have in common, if we take out that S sub n, we end up being left with 1 minus R on this side, and then we still had the first term times 1 minus R to the n on the second side, which, if we divide everything by this 1 minus R to get S sub n by itself, we end up getting our formula, right? Because now this cancels out, and we're left with our sum being equal to our first term, 1 minus R to the n, all being divided by this 1 minus R, okay? So this, using that example, is the derivation for our geometric series sum. And again, we can use this to help us calculate that sum for even one like Shelley's, right? Where we have some of those first 9 terms. We could take first term, 1 minus that R value, in this case to the n power, and then all divided by 1 minus that R value. So I'm going to take, go back to my calculator, 8, 1 minus my R value, which was the square root of 3, divided by 2, and then that, specifically just that piece, is to the 9th power. And then I'm going to make sure that then I divide that by parentheses 1 minus my R value, which again is square root of 3 over 2, to get my summation this time of just about 43.351. So close would be my sum of those first 9 terms. Now, we will definitely be working more with these in class, but you want to definitely make sure you have down this summation formula for our geometric series so we can use them in class. And again, I recommend some parentheses around that as you write it down. Thanks everyone for watching. We'll work more in class.